afternoon, good evening, or good morning from wherever you're joining us from today in the world. My name's Sarah and I'm the Program and Event Manager at the Reactor in Sydney, Australia. Welcome to another Microsoft Reactor Sydney live stream event. So today we'll be doing episode 3 of our What in the Wordle series, which is hosted by our regional cloud advocate, Renee Noble. So for those of you that are joining us for the first time today, a bit of background on Renee. So she's a self-proclaimed Jane of all trades, and she's worked in government doing ML and Python backend, full stack in the ed tech startup sector, and dabbles with embedded tech. In her spare time, she leads the Girls Programming Network for women and girls to realize their potential as techies. She's also started a business to help bring exciting coding opportunities to kids and teachers in her spare time. Today, we'll be speaking for about 45 minutes to 50 minutes with hopefully 10 minutes for questions at the end. However, if you've joined us before, as you know, please do ask us questions throughout in the comment section and we'll try and answer as many as possible. We'll also share with you a link to our feedback survey with the event code for today, which is 15716. We'll put that into the comment section shortly. You'll also see I've also put the additional resources and learnings from today's session that have kindly been provided by Renee in the comment section already for you to check out either after the session or during if it's applicable to any sort of demo that you're doing today in the session. We'll also be recording this session and there will be an on-demand version available straight up today on our YouTube channel, which we'll share with you the link to later on. But for now, I'll hand the floor over to Renee to begin. So thank you, Renee, and over to you.
Thank you so much, Sarah. Excited to be here for our episode 3, Solve Games of What in the Wordle. I love calling it What in the Worldle, because I can't say it, Sarah can't say it. It's just terrific. It rolls off the tongue. So love that aspect of every week. So yes, this week we're going to be looking at how to solve games, because last week we dealt with the first word dilemma. What's the best word to start with? Adu, audio, crank. There's a lot of articles going around the internet with opinions on this, and we made up our own algorithm for calculating the best first word for you. But that leaves us with the rest of the game to play, and maybe we've had our first word suggested to us. What if the computer just played the rest of the game for us? That would be convenient. So yeah, we dealt with these graphs last week. We made these fabulous graphs that showed us word, letter, importance in different positions and how often the letters are used in words, and came up with our own first words. Maybe it's tears or rails or Laris, or maybe it's whatever you wanted to calibrate your algorithm to give you more vowels, more consonants, etc. We're going to be jumping off with that algorithm still in our pocket this week, as well as the what we made in our first episode, the Wordle game that we created in Python. So today we're going to be grabbing our original game and putting it in a class. We're going to be dealing a lot with classes and functions today, just because, yeah, we're going to talk about classes, why they're going to be useful, but we're going to wrap up our original game in a class, and then, it'll be nice and convenient for use with our solver. We're going to bring in other functions we made along the way, because we made some really good, graph functions. We don't need the graphs anymore, but we do need the data that we've been working on grabbing, as well as things like making those beautiful green, yellow, and black love hearts for displaying our Wordle answers. So I'm going to grab those. We're going to bring those into, we're going to start creating our solver class first, and then we're going to look at what data we're going to need to get started with that, because you look at a game of Wordle and you go, there's a lot of different yellow and green and gray letters here, but how do we actually store this data? What data is actually available in there? It's really easy for the human mind to process and use it in particular ways, but you need to get a lot more explicit when you're dealing with computing, of course. So we have to work out how we're going to store that and what's available to us. And then we're going to use info from these previous guesses that we're making. So throughout the game, we're going to keep getting those yellow, green, and black love hearts, and we're going to see what they give us in terms of our information. And of course, we're going to need something that chooses a guess for us. So we're going to, grab what we had from last week for choosing our first guess, and then we're going to see what changes we need to make it suitable for guess 2. So let's jump straight into putting our game in a class. So jumping across here, make this a little bigger for you all. If you are coding along at home, this scaffold is already up on GitHub. If you want to grab it in episode 3 folder, it's all there for you, because we're going to be filling out this today, because just to give you an idea of what we're doing. We're going to add our helper functions up the top here. We've got some calls to them already. And we've got some data we had from last week, previous weeks, with just, keeping our variables, getting them set up. And then we've got our classes. We've got our game one, which is a little itty bitty one to get started with. And then our solver, which is a little bit more complicated, but it's all going to make sense, I promise, when we go through it. And we've got the rest of the hour to do it. So let's get started with the game. So previously, we had our game from episode 1, and we had the beautiful love hearts printed out so we could make a guess, and then it would show us what the correct and incorrect spots were for the letters. So I'm going to actually just start by grabbing the code that we had from that project that we made. So I'm going to grab what I'm going to call the play function. And just whack everything in there that we just made the last time. So if you didn't watch for episode 1, check it out. It's pretty fun. I like it. And I'm just going to get rid of this part for now. I'm going to bring this back in. So this is what we had previously. We had that you input a guess, and then if the guess isn't in the allowed word list, it's going to keep asking you again. Once you have an allowed guess, then we are going to print out the guess, and we're also going to print out the color result of the guess with the green, yellow, and black. And then we keep doing that for 6 turns with our for loop up here. And then if we get the correct answer, we're all done. We escape that with the break. And if we get all the way through our 6 for loop loops without getting the right answer, then we print it bad luck. So there are some things we're going to add to this, which is notably these 3 lines. So we haven't got to that part yet, but we'll talk about that now. So we also want to get some data in here. So we've got our code in here, but let's jump back to the slides just to talk about classes just for a minute, because why do we want to use a class is like a useful question to talk about. If you haven't used classes before, I kind of think of them like an orb. As you can see here, I've got my cat orb, and it's got things that I'm going to call in this example facts and actions. So we might have facts like the name of a cat, the age of the cat, things that the cat likes, a list of them, the color of the cat. You might also have actions that you can do to the orb. You might want to rename the cat. You don't like Tinkerbell. You bought this cat from, the RSPCA, and you're like, this is the wrong name for this cat. I want to call this cat Mr. Fluff. And then you want to update this name, so you could call the action that is called rename. Or maybe you want to add a thing that they like to this data collection. So you'd call add like to add the like of beef. And it would be added to the list if you coded that method, what they're actually called. So the reason we want to use this is it keeps all our data kind of together in a bundle of things that are related. And when we use these actions, it uses that internal data. So we don't have to be passing all of this data in and around to make these decisions and do these algorithms. It helps the code be neater because we can just say things like cat.name. It's very readable, or cat.rename, or whatever you call your variable. Maybe you want a specific, name for your cat. So, and then finally we can have multiple instances of cat or whatever class you've come up with. So you might have Tinkerbell, soon to be called Mr. Fluff over here, and BB, which is my cat. And they have the same properties that are here. Attributes, as we actually call them, attributes and methods, what we call them. And we can say cat.name, and it will say Tinkerbell, or it will say cat.age, and it will give us 7. So it gives us this shape of the data that we can easily interact with. But actually, we don't really care about having multiple instances today, because we're going to have one game and we're going to have one solver. So the reason we're here is to keep our data neat and together, and have it be able to enact change on that data as we play the game, and we want to update it all. So that's what we're going to be doing here. So jumping back, when you have a class in Python, the first thing you want to have is your __init function, or DunderInit as we call it for short. So right now I've got it set up to just skip past this, but what we're going to want to keep for this game is a few bits of data. So I'm going to just pop these in. I'm going to talk through them. So whenever we want to give a property to the class, we say self dot and then whatever you want this attribute to be called. And we're going to start by saying this game class has an attribute called turns. It's also got attribute called results and allowed words, and we'll get to this in a second. So we want to say, okay, we haven't had any turns yet. This is where we put the guesses. And then we have, here is where we keep our love heart results. Green, yellow, black stuff in there. So we know what we got for each guess. So we'll have up to 6 things in here. Then just up here, I've called some functions. We haven't put these in yet. We'll put those in just a second. But we want to get a thing that's get all the words that we're allowed, because we're going to want to have access to all of those for our game. So that's just up here. And finally, we want to generate an answer. So this is a method. So when the DunderInit function gets called, the method gets called when you create a game instance of the game class, then it does all of these, and including this method call here. So that's going to jump down to this function. So previously, we had some code that looked like this. It's just got commented out there, but it looks like that for what we had when we created our game. We just uncommented. We'll get that nice syntax highlighting. Ooh, that's not what we wanted at all. There we go. So we've got open the official answers, which is a file we've got over here on the side. And then read all those things, split it up, and then choose something randomly from that, which is really cool. We could just have random game after game, but just for now, just so we always know what the thing is going to be, I'm just going to manually set it. It's going to say set answer to hello. So we can see that we're setting self.answer. When we have a method, we always have the self parameter there, because that means, hey, you can change this class that you're talking about, this instance of the class. So you can set the answer to be hello. Cool. Okay, so we've got most of our stuff there for the playing the game. So we set it up, we set an answer, and then we play the game. But because we're going to be wanting to use, instead of input from the user, like we could actually play this now. Let's actually give that a go. Let's see how it goes. Maybe the code will be not happy. Whoa, wasn't expecting that. Is it in debug mode? I'm not sure. Something's happened. Stop debugging. Okay. Let's just make that go away. Okay. Let's try that one more time. There we go. That's more normal. Great. Okay, so we have to give it a solver, because I've told it we have to give it a solver, but we're not actually using it yet. So I'm going to take that out, and we should have a game just like we did before. So I'm going to say tired. Okay, well, it nearly runs. We have left out a couple of things. We've made a couple of changes here, but yes, of course, because we haven't actually got our allowed words yet. But theoretically, you could, once we have our allowed words, which we'll get to in just a second, make the game class an instance of game, and then go game.play if we had all the words that we needed to load. But we haven't done that yet. So, yeah, but just before we jump up to actually getting all the words that we need, we want to not have it as a guessing game. We want it to actually take in a solver, because that way we don't have to play it. It'll just play itself. So when we call this method, I'm going to say, we're actually going to give you a solver, which is going to be a whole nother object, another class or instance of a class, which we're going to pass through, and then it can use it throughout and call things like make a guess. So we're going to be setting up something that does this. So you're going to get the guess by saying what, instead of asking the guess is from input, we're going to ask for the guess from the solver, which we're going to create in a minute. And then we get to make sure we can actually play the game with learning new stuff as we go along. We're going to give it all of the turns that we've previously had. As we said, we've set it up in here. We've got all the turns we've had so far and all the results as well. And then there's only one last thing to do, is to say, after we've had our guess, we want to add that guess to the list of turns. And we're going to get the color result, which we'll get to in a second, which is our yellow, green, black love hearts. And we're also going to append that result to the results list. So as we go along, we build up the results and the guesses we've had so far. And that means each turn we can pass them back into the solver, because it needs to have the context of what the game looks like so far. So let's jump to our beautiful functions that we made before. Before we made this lovely function, it makes these printed out love hearts for us. We also made our functions to do with getting this data. So they were useful in those episodes, and they're going to be useful again now. So we're going to go and jump and grab all of those as well. Yeah, we've already done a lot of the code that we needed to do for this. We just need to bring it in and make it in a nice, useful, like clean cut, easy to get to way, because in episode 2, we had all of our code in the IPython notebook, which is really good for experimentation, but not necessarily good if you want to be able to load it in with something else or run it as one big contiguous program. So I'm going to start by getting all the words, which we started in the first episode. Just got another line in here where we could do a test. So we might test it with a smaller set of words, just to 10 words to see how it's going, especially if some bugs come up, because that dealing with 17,000 words at the same time and trying to work out where the bug is a bit of a pain. So I'm going to leave that line in there, and I'm going to make sure this is actually the name of the file. So we've got get all of the words here now. So, and then we return a list of all of the words out of the file. So we have them here, all of these words in a big list now. So that's what we want for the game, so we can start making guesses that belong to that list of allowed guesses. So that's from the first week and also from the second week. We needed the words all the time, but we're also going to grab a couple other things from episode 2. So if you haven't used default dicts before, I would recommend jumping into episode 2 and learning about default dictionaries. They're really useful. As you can see at the top, I've imported default dict from collections, as well as some other things over here, which I'll talk through in a second. But yes, string and ASCII lowercase, I'll just mention this now, is just how you get the lowercase alphabet. So we need that at some point. Okay, so this one here is counting up how many words each letter appears in. So looking at all the words, how many of them have an E? A single, multiple E's, doesn't matter. How many have an E or an A or a J or a Z, etc., and giving us that count. So we need this for when we're making our guesses later, so we can calculate what might be the best guess. So this came from our working out the best first word guess. So let's get this next one we did last week as well, which is the position count. So how many times does the letter E appear in the 4th spot or the 5th spot, or how many times does the letter S appear in the 1st spot? So that's how we got one of the graphs. Oh, not that graph, but up here. Yeah, so these graphs come from that data. Okay, so we've got that now. There's only 2 more that we need. The color result. So this is where we get our green, yellow, black love hearts from. It's pretty fun to implement. It looks quite big for what it does. Do jump back and watch episode 1 if you want to know more about this. But it just goes through the word, starts with the things that are green. Should this be green? If not, take a note of it. Note down the green ones. Should it be yellow? And then everything else is black if it was not any of those. Lastly, the teeniest, tiniest function. This one's just for clearing the screen. We might not use this until the very end, just because we want to be able to see all of our code for the debugging. And in practicing for this one, I realized, the clearing screen is on, so I can't actually see any of my printing out to see if I've eliminated the correct letters and things from all my debug print statements. So that is all of our helper functions from last time. So we've put these as helper functions because they don't necessarily pertain to the game or the solver. They're just kind of generic do a task function. So I've put them out here. We could possibly have done color result as a method of the game function of the game class, that because we already have all of the guess and answer information in there. But just for simplicity, I'm just leaving it out here. And yeah, the rest of it's all about words and data and files and things. So they just really pop this code out of the way and then be able to call a nice short tight function name to get it into your code. You might also, if you're making something like this, a game solver, generally you might want to separate these things out so that you have different files. So you could have the solver.py file and then game.py file and the helper functions file. And then we could import all of those. But just for the simplicity of the stream, I'm putting them all together so we can jump back and forth between them without having to switch tabs so many times. But I am going to collapse these ones up just because they'll be out of the way until we want to maybe look at them again later. Okay, cool. So we've got our game function and it looks all good to go for me. So let's actually pop this out. Let's see if it still works with the input, because that's a good test to do to see if your things work first before you try and solve something with them. Allowed words.txt isn't existing. Allowed, what have we done? We need to CD into episode 3. If you're using VS Code, this is my hot tip. That you might sometimes go, why is this not working? And it's because you're just in a directory up from where you're trying to call something. So let's give it another go. Okay, here we go. So if we go tiers and sphere, etc., and it seems to be working. Carts, create, crate, that has the right number of letters. Spoil, and hello. We did it. We have our code that looks like this. But I've turned off our clear screen just so we have all of this so we can see our guess and a printout of the whole game. So that's all working. So let's pop these back and get to making the solver that we are calling here. So let's get rid of that. So no more guessing. The solver is going to do all the guessing and it's going to be our input for this function rather than us doing it. Okay, so let's jump back and see what the slides say we're doing next. Okay, so time to solve the game. So we're going to make a class for our solver, and the things that we want to keep track of, which I called, I don't remember what we called them, facts about our cat, actually called attributes. And we're going to have a list of all the possible words that are remaining. So as you get more guesses, this is going to get narrowed down. And then soon there'll only be a couple of words that could potentially fit. Just so we don't have to do that full processing every single time we go through. We could do that with all of our data, but it's easier just to get rid of them as we cull them out of the selection each single turn. So we've got that. We've got the fixed letters. I'll get to what this means in a second. The letter position info and the letter min max. So these are the bits of data. I'm going to tell you what these bits of information are going to be and why I've chosen to have these ones. For the methods, what are called actions before, we have the guess. So make a guess solver using information from the previous guesses and the results that we've seen so far from the game. Then we also have update guess info. So by looking at all the info from the game, so from the last turn, adding that to our collection of information, what new information do we have that we can store and then use to make our decisions to eliminate the words, which is our next one. And finally, score possibilities, because we're going to have a bunch of words left most of the turns. So we're going to have to decide which one we're going to do next. And we're going to do that based on what we did for our first turn. with a small adjustment for the second and ongoing turns. But you could actually put in anything here, and that's what we'll also look at next week when we get to that episode called Robot Brain. So what kind of information do we have that we need to store is the question we have here. So there's some obvious information. There's no B in this word. It's grey. The O is in the correct place because it's green. And E, there is an E in the word, but it does not go here in the fourth spot. But there's actually more information we can see from here. For instance, O is in the correct... that one should be updated. There's not two O's in this, we can see, because we know it would be yellow or green if there was. And we know that there's exactly one O because it's grey. But also, we also don't have information from this O, for instance, because we don't have the other O present. So we could be like, for instance, if this wasn't an O, it was another letter that we hadn't ruled out up here, we couldn't say, oh, well, we know there's an O in position 2. This wouldn't help us because it's like, is this the O from position 2? Or maybe this is another O from the end of the words. Imagine the word was bongo, like bongo drum. Like, could that be that letter? Or is it this letter? So that doesn't actually give us any new information. So looking at the data we get in the guess responses, we can work out what information is available to us. So from this sequence of guesses, we can say there are a 0 of the letter B. We can say, because that's grey, then we can also say there is at least one E. We don't know how many E's. There might be up to 5. Not really, because we've got other letters, but potentially E's everywhere. And then we can say 2 of O is too many because one's grey. There is exactly one O. We can also say E can't go in this spot, in the fourth spot. And O must be in spot 2. So if the word doesn't have O in spot 2, it's just right out. So there's kind of 2 groups of information. There's like how many of something is here, and then there's where do things belong specifically. So I've come up with a way to separate those 2 bits of information and then tie them together to make our guesses. So firstly, let's look at the left here. How many of a letter are there? So there are 0 of B. So we can say there's a minimum of 0, and there's also a maximum of 0 here. We can also say there's at least one E. So there's a minimum of 1 and a maximum of, well, we don't know what the maximum is, but 5 is what we're going to set for the default. And then 2 of O is too many. So it's got a maximum of 1, but we also know there is exactly 1 because we have the green O. We also have the other side. E can't go in the fourth spot. And we have O must go in spot 2. So we can see in here, if we start with B, which we know there are 0 of them, so none of the spots are acceptable for B. Then we have O must go in spot 2. We also can't go in spot 3. We could also infer that it can't go in any of the other spots, but we haven't tested them, so we could fill that out, but our other collection of data kind of processes that for us. So we could go to the effort of putting them in here, but we won't bother. Then we've got E can't go in the fourth spot. We don't know about the other spots. We know it's going to be in there somewhere from the data in the other one, in the other table that we had, but we know it doesn't go in the fourth spot. So from this, we could work out what things are green. And as we build up more greens, we could check our ever-growing table of letters for where things have to be. But just for simplicity, we're also going to have something called fixed positions, just so we can easily quickly run through something and check, are all the things that we know are green in the right spots without having to search through this entire chunk of table, really. So that's what we're going to do for storing our bits of data. So let's jump to that and get that happening. So we're going to start by setting up these bits of information in our init here. So get rid of the pass, which just lets Python skip over things and not freak out about the indents that are there. Then I'm going to grab something I prepared earlier. Okay. So first up, we want to have as we said, all the possible words. So just like we have for the other class for the game, we're just using all words here again. Okay, then next up, we want to have the fixed letters. So I'm going to start this one out with a list comprehension. So the fixed letters for the solver are the none, which is like the null piece of data, repeated 5 times and stored in a list. So just none, 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 none. And we'll update this as we go. We also want to have that position information. So for this one, it looks a bit long, but it's very friendly and nice. So what we're going to end up having here is something, we might have the letter A, and it will have, once again, we're using that list comprehension to get a bunch of none. And then we have the same kinds of things for B, etc. And as we go through, we will replace these with false and true. If we find out something has to go in, if there has to be an A in the 5th spot, then that will become true. If we know there's no A in the 3rd spot, that will become false. Until we know something, it will be none. So that's what that one will look like. Yep. Cool. And then we have, let's chuck this up here just so we can have that on hand for later. We want to look at it. Okay. It's never hurts to have an example of niche data structures in your code. Okay. And here we go. Another list comprehension. Well, this is a dictionary comprehension. This one was a dictionary comprehension with a list comprehension inside it. So it looks a little bit tricky. This one we have for each letter in the alphabet. Then we have a minimum of 0 spots, 0 occurrences. So it might have no occurrences, or it might have up to 5. Not that there's actually any words that have that many, but it doesn't matter. The things will get ruled out later based on if we find out more information, or simply if you have to have 3 E's and 2 T's or something, you know that anything else is not going to get a chance to jump into the word. So it balances itself out, even if we don't update this 5, if we don't, for when we find out more green letters. Because we could say every time we find a green letter, we update all the other letters to say there's 1 less possible spot. But we're actually not going to do that because it's not necessary because of the other logic we're going to include in our solver. So we've got all of our data here, and we now are ready to start eliminating words. So yeah, we've got all of these things which we're going to fill out throughout this. Please do remember to ask questions at any time so we can jump to a piece of the code, and I will happily elaborate on anything. So what we have to do next is, what words can we eliminate? So we need to get the data from our guesses and eliminate words because we know it doesn't have a B in it, or it has to have an S in the last spot. So we can just eliminate a bunch of words, heaps of words at a time, if we know the word doesn't have any T's in it, for instance. So let's start by doing that. And I'm actually going to start by doing 3 sub methods. They're not really sub methods. I've put this underscore in front of them because that's the Python convention for saying this is something that's designed to be used internally by other functions, other methods of the class. Probably don't want to call this from the outside. So we wouldn't want to go solver dot fixed letters correct because it's been marked with this underscore. And that's not to say that you can't. Python's attitude is we're all adults here. So if you really want to, you can definitely do that. And if something's super like you really don't want to use this, you might even write a double underscore there. But we've just gotten the single underscore, but you know, we could use it later if you wanted outside of the internals of the class. But yeah, so we've got 3 different things that I want to work us through today. So firstly, the first one's the easiest one to get through, which is the fixed letters are in the correct spot. So if we have something that's green, we can check every word in our list and say, is this got a green in the right spot? If we know O has to be in the second spot, then there's no point in looking at any of the words that don't have O in the second spot. So let's grab some code for that and talk through it. Okay, here we go. Okay, so we're going to take in a word, and we already have all the information stored in the class object that has all the information about our guesses, because we put that all in up here. So we have access to what the fixed letters have to be, any other information. So it's just all there for us to use, which is really convenient. So we can ask the solver, for this word, can you check if all of the green things that we know are green are in this word in the right spot? So we can go through our word. We're using enumerate again, which we've used in previous weeks, which is a way to say go through each letter, but we also want the index of each letter. So 0, 1, 2, 3, 4. Put that into I as we go through and give us the letter at the same time. So we would go through, and then so here we go with firstly checking if the fixed letters. So first we want to say, go to this spot in our fixed letters collection, which looked like this. And if it's not none, we've got question mark here. And then so if it's not none, so we know something about it, and the letter is incorrect. So we know O has to go in the second spot. If there's a J here, that's definitely wrong. Then we want to return false. If we get through all of the letters and we get to the end, then we know that they were any of the green letters were in the correct spot, and we were going to return true. So that's our nice and simple, go through all the letters, check for the greens, and tick it off if they're all good. And then you return true, saying this word is a possibility based on the fixed letters in the correct positions. So that's part one. We've got 3 of these different ones. We've got, next up, no misplaced repeating. So what this one is about is, say you've said, like we had here, E can't be in this spot. So we don't want to look at any words that have E in this spot because they're not useful to us, because that's definitely out. So once again, we're going to grab some code. Very similar structure. It's really just the condition here that we're changing. So we're looking up different data each time to work out what should go on there. So in this instance, we're saying, okay, go through each letter in the word. So maybe we've gone for bones. And we'd say, okay, firstly, let's look at letter B, which is in position 0. We're going to look it up in the list we created earlier, which we'll jump back to for a little peek. So that's this one here. So we say, okay, look up A. And then in the list for A, or B, because we're doing bones, go to a particular spot. So maybe 0. And then you can check if it's none, false, or true. So then we can say, okay, if it's none, if it's not none, so we know something about the information, so it's either true or false. And if the fixed letter, I'm in the wrong one. Here we go. That's better. So we can look up that position and that letter and that position. So we'll look up A and the first spot in A, or B and the 0th spot. And if it doesn't say false, or if it does say false, we're like, oh, this word's no good. We can't have below because it has a B in the first spot. And we already tried B for the first spot, and we know it maybe doesn't go there. So we're going to say false to this word. It's not okay. If it is okay, we would move on to the next iteration of our loop, which would be O. We'd do the same. Is O allowed here, etc. All the way to the end of the word. Once again, if we get through all the letters and we haven't returned false, because we will end our method as soon as we return false, if we get to the end, we return true. Say, this is a valid word based on the no misplaced repeating letter principle. finally, we have letter counts in range. This one looks just a little chunkier, but it's basically the same. So what this one does a lot of carrying actually, because not only does it say for that instance where we had 2 O's and we know that one, there's exactly 1 O, it also covers the case where we've eliminated a letter. So we know in this case that there's no B, so it's 0 and 0. So we're checking for all of the letters in the word, and all of the letters that we know about. Have we got enough E's? Have we got enough O's? Have we got too many O's? Have we got too many B's? And too many B's in this instance would be any B's at all. So this one is actually covering, don't include any letters that we've already ruled out, as well as those instances where you might have double letters that you need to have doubles or don't have doubles of, etc., where we have that information. So in this one, we are going through the letter min-max. So that one looked like we had our dictionary, and then we had something like A, and then we would have our list of things. I made this a list rather than a tuple because it's immutable. Tuples are immutable, and I do want to be able to update either item here. You could have a dictionary and have min-max as well, but it's a simple idea. So we'll just have our list here, and for instance, we want to look through here and find out for each letter in the alphabet, so we have A, B, C, D, E, F, G, etc. Have we covered in this word enough of the required letters? So do we have 2 O's? Do we have exactly 1 E? Do we have 0 F's, etc.? So this one gets rid of those ruled out letters. So we go through each letter, we get that min-max pair, which would be 1, 2, and we get the letters. So it might be A, 1, 2. We get this as part of our min-max. And then on the next line, we're actually just going to expand that out into min letter, max letter. So we'd have 1 for min letter, 2 for max letter. Now we're going to use count, which is just a handy little method of a string or a list to count how many of a specific letter is in there. So I could do, let's do a little practice in here. 3, just down the bottom here, I'm typing, we have triple A. It will tell us, if we do count, how many A's are in here. It will tell us that there's 3. We could do the same for V. We could do the same for a letter or a number that's not in there. Anything, we could check that's not in there or is in there. So we're going to get the count of how many things of that letter. So we're starting with A. How many A's are in the word? Is the number of A's less than the minimum or more than the maximum allowed number? If it is, we're going to return false because that word clearly does not satisfy the requirements. If we get through every letter in the alphabet and we've satisfied that there's enough of each thing that we're looking for, then great. We're going to return that option is a possibility. That word is okay. So those are our 3 different parts. Now we just got to set up actually using them in our eliminate words area, in our method for that. So for this, we're going to kind of rule it out one at a time based checking on the method. So we're going to check a word for each of these different items, for each of these different methods. And if it fails one, we're just going to skip that word because we don't need to check the other ideas about that because we know that's already been ruled out on one measure. So I'm just going to grab us some code for that. Okay, so this one has a fairly simple pattern to it. I'm going to just chuck it in here as one big chunk. Okay, so we got our new possible list of words. So here we've got nothing in here so far, but as we go through, if something passes all 3 tests, it's going to get added to the list. And at the end, we're going to say the possible words is the ones we found during this function here. Inside this method, I should say. So what we're going to do, the structure I've set up here is we say if not, so if it fails the test for fixed correct letters. So are all the green ones correct? We're going to continue. And what continue does in Python is it says, skip the rest of this loop. We don't want to finish it. We're just going to go straight back to the 4, do the next letter. So we don't get the thing added to our list. It just skips all the way around. Okay, so then we repeat that pattern with misplaced repeating letters. So have we used the yellow letters that we have in our words in different spots? And then finally, are all the counts in range? Don't use anything that we're not allowed to have because we already ruled it out. And it's all those double letters and things, or things we have information on the minimum and maximum amount correct. And then if it passes all 3 tests, we get to here. And then finally, at the end of adding all of our words to that new list, we update our possible words. So that one's all good to go now. So I think that's eliminating words. We have more slides. So we've done fixed letters are correct, and we've done letters have been placed in the right spots, placed in new spots rather than repeating old bad habits. And finally, min and max letters, min and max occurrence of letters. So now that we have that all working, we can pick a guess. So what we're going to do is we're going to grab our guess machine from last episode as well. And then just make a small get change on that one. So jumping back to our code. Grabbing our guess maker from last time. And we've already got all our helper functions here for this. So we're going to need our score possibilities. That's what we need to do first. So our guess is based on scoring the possibilities, which is exactly what we called our function last episode in making our scoring system. So what we did in that episode is we looked at things like vowels, consonants, and those graphs I've shown you before. And then we kind of rated them based on like how much we want vowels, how much we want consonants in our starting word. And then how important it is to have, highly popular letters in your starting guess, as well as things that, always putting an S in the last spot, because more than 50% of 5-letter words have an S in the last position. So giving more points based on that. So this is it's just a function I made up. It's not, very scientific. Well, it's got some data analytics, which is a good basis for it. But at the end of the day, we haven't really weighted or done an experiment to see how much more important something being in the right position is to Wordle, etc. So this is just a way to start choosing something. And you could replace this with any score possibilities, any scoring function of your own desires. So at the end of it, we give back a sorted list with a score, a word, and a score for each of them. And then we're going to start by taking the first item of that score, the list of possibilities with their scores, because we've sorted it so we get the best one first. So jumping up to our guess. This one's a nice simple function because it's got not a lot going on, because we've done all the heavy lifting in that other one down the bottom. So let's start off with the first letter case, the first guess case, which is just call the function and get the first thing in the list. Get the first pair of word and score, and then just get the word. That's what this is. So this is get the word and score, and then this is get just the word because it's the first item there. So that's what I want to do for the first one, which is just call the function we set up last time. But for subsequent guesses, something we had done in the first guess is I didn't want to use any repeated letters because I don't want to waste spots being like putting a bunch of E's in it just because they're a popular letter in the alphabet. I want one of each letter to help me rule out possibilities. Maybe you don't want that, up to you. But for the subsequent guesses, it's entirely possible that our word does have 2 E's or 2 O's or 2 T's in it. So if I were to rule out all those options or score them really badly, then it would be a problem. So for this part, what we're going to do is I'm going to pass allow repeated letters. So you can see this line here. Let's get rid of these for now. This line here is the same as this, but I'm going to scroll back down to show you that I've added a bit of code to allow us to have repeated letters. So here we go. So we assume you're not allowed to repeat the letters because this is our first word function. But if you are, if it's not false, so you're allowed repeated letters if you're allowed repeated letters, and then we want to ensure that we don't negatively affect it. So yeah, we've added just in this bit of code here to prepare it for subsequent guesses. So turns 2 through 6, or hopefully less than 6, that means we can have our repeated letters in here. So back to the game, to the guessing work. Okay, so that's the difference between those two. The other things we need to do when we make our guess are we want to get the eliminated words. We want to eliminate words from the possible words. And then I'm also going to print out how many possible words there are left, because that's interesting, because you start out with 17,000 and then quickly you only have 100 and then you only have 8, and it's choosing from a very limited selection. So there's only one more thing we need to do before we're kind of ready to go, which is update guess information. And this kind of part is a little tricky looking. So let me just grab that function. So this is where we go, okay, we need to look through all of the data that we have gathered. So this has several parts for updating our different parts of the data. So I'm going to copy it all in, and then I'm going to comment some parts out as we go through them. So let's just, yep, that's all ready to go. So don't forget to actually add our updating information in there for later. So, okay, let's have a look at this function. Let's get rid of some of this first. Okay. Okay, so here we go. We're looking at the guess and the results. We're going to use zip. Zip as a way to say we have two lists of things. I want them to be zipped together because they're related. So if I had let me turn Python back on here. Python 3. I hope this is big enough for you all to see. I'll make it a little bigger. For this example, I don't want you debug console, but you're here for some reason. Okay, so if I had A and it's equal to 1, 2, 3. Whoops. 1, 2, 3. Okay, and then we have B and it's equal to A, B, C. Oops. Oh, I hit enter, but that's okay. It'll be fine. Let's print it out and make sure. Great. So if we go zip A and B, it gives us, where did A go? Oh. Let's try again with A. Okay. Zip AB, and then if we do list, zip AB, then we get a thing that's got them all bound together like that, so we can have them all at the same time. That's what zip is doing there. Then we are going to actually get those list, letter, and pair out together. This has just been a way to handle them both in parallel at the same time. And then if the result is green, then we're going to set the fixed letter for that letter to fixed letters for that spot. So we've got the 5 spots. You can say, okay, we now know the 4th letter has to be F. And then you would say, let's lock that in our fixed letters. And we're going to update that information that belongs to this instance of the class. So next up. So what is this one doing? There's a lot of stuff in here. Could use more comments. Let's find out what it does. So we want to say, okay, so we've got the set of fixed letters. So that's working out if there's any duplicates in there. For letter in letters, if the letter is not none, so we're going through the list, the 5 bits, we want to check that the looking at the guess, we want to make sure which ones have have extra things. So we want to update our min and our max based on the maximum count of green or yellow things in the word. So if we had 2 greens, we'd be like, okay, well, there's definitely 2 J's. So J's wouldn't be 2 letters. I wonder if there's any words with 2 J's in it. But yes, there could be 2 J's because we've got 1 green and 1 yellow. And we want to do that based on the fixed letters that we've just done. So we've set up the fixed letters. So if we've locked 2 things in, we can use that data instead of going through the love house again. We just look at that data and say, okay, this needs to be updated to ensure that we have this many letters, this many instances of the letter J in any guesses we're going to deal with in the future. So this is updating our data so we know that for the future. Okay, so lock in min, max from the fixed letters. Okay, so next up, this one is about, so we're guessing with the repeated letters, can we reveal the exact number or the minimum? So this is like that instance where we had the double O's. We want to make sure that we update our count. So these parts are all going to come together. So we're going to get the count of the letters. For each of the results. We're adding all the results. So we just want to have for each letter. So what we're actually trying to make is we might have A, and then we might have, I don't have all the emojis on me, but we would have the various different emojis of the hearts. And then we could say, how many of these are the green hearts? How many of them are the yellow hearts, etc. So the count letter results is going to give us that of counting up how many green and yellow are there in there. So to make this, we're going to say for each letter in the group results, where did we make group results? Somewhere up here. I feel like we're missing a chunk of code. Okay. Okay, yes, we're just splitting it out. So we've got the letter and then the results to go for it. So that is, for instance, we've got the letter A and then the group results, which is like how many different, there was 1 yellow and 1 black for the A's. We know there's exactly 1 yellow in that, in the correct guess. So we're counting up those items. And then if there is a black in the group, we know we've got a maximum. And therefore, we know we've got the exact number of things that we need there. Just like we had with that first example where we had the 2 O's. We had 1 black and 1 green. We know there is exactly 1 O in the word then. So we can then set the min and the max number to that. So it might be 1 or it might be 2 if you tried a word with 3 O's in it somehow. Then you'd be like, okay, well, it said it had exactly 2 because we counted there were 2 greens. There was 2 green and or yellow things in there. So we can update that. If we don't have a black, we don't have a maximum, but we do have a minimum potentially. So it's like, oh, we've seen that there is a minimum, the 0th item in that list, because we have seen that there is at least 1 E. So we're going to update the minimum. So finally, we need to update the position information, which is saying, okay, we've got the word, we've got the guess and the results for each of those letters and their result. Then if the result is green, then we can say, yes, true to that. If it's not green, then it's not supposed to be in that spot. Whether it's not supposed to be in the word or not supposed to be in that spot because it's yellow, doesn't matter. We're just saying it's false for that spot. So now we have our whole thing ready to go, I think. Let's make sure we haven't missed anything. Those are all collapsed because we're done with them. So hopefully, this is all going to run now when we press the go button. Okay, and we're going to turn on the solver. So we're going to instantiate our solver. We're going to pass in the solver. We're going to actually say that our game takes in a solver. I think I got rid of that. Where is the game? Okay, no, it's got it in there. Okay, fingers crossed, everybody. Let's open up our window and get out of Python and then run it. and we've done it. So it's guessed hairs because that's our favorite word. We've gone Louis, Pelon, cello, and hello. And so we could, of course, change this to be any other spots, any other words. Here we go. We could do squid. We could run it again. Yeah, and then we go 4 guesses to get the right one. So yeah, Sarah is asking us a question in the chat. Getting complicated. I'm going to have to step through these with the debugger to work out what's happening, but I'm really enjoying trying to follow along. Thank you, Sarah, for the comment. Yeah, and I'm just really happy that it all works. We're of course going to improve this next week because as we know, as Wordle aficionados, we know that something like Scooty or Scuddy, I don't know how you say it, isn't going to be the answer because the words that are the answers are ones that are commonly known, or at least fairly commonly known. So we wouldn't guess this if we were trying to actually go for the answer. And maybe this is useful if you're trying to just get more information, but if we had a limited number of words, so on this previous guess, we only had 7 words left. We could print them out and find out what they are. Potentially, but we're out of time, so I'll leave that for an exercise for the viewer. But squid is probably going to be the best one in that list of 7 words, so maybe we could actually have got this in 3 guesses. So next week we're going to be looking at how we can best make those decisions with natural language processing, because by looking at different language, like the use of language, we can see what words are common, what words aren't, and what words are more interrelated to each other. So we're going to be doing something called natural language processing, NLP, word vectorization. And with those, by turning words into numbers that represent the space that the words relate to each other, you turn it into an n-dimensional vector. We can actually see how far away 2 different words are in terms of their numerical space value. So we're going to be doing that to see if we can make better guesses next time on the final episode of What in the Wordle. So I hope you join for that. Do jump on to GitHub to grab today's code. It's all on the link that I think Sarah has already shared in the chat. So jump on there, grab the links to the resources. There's super useful, if you want to practice with classes and functions. We've got that up on MS Learn for you to give those a go before you delve into this world of a lot of classes and a lot of methods and functions if this is your first time dealing with classes. And jump on the site and register for next week so you can come and see the natural language processing fun. And we'll see you there, I hope, fingers crossed. And we'll be, you creating an Azure ML endpoint using natural language processing, the word-to-vec model on Azure. It'll be super fun. But
Thank you very much, Renee.
Sarah has turned into Michael.
I have. She's morphed and I've become the new host. So thank you very much for another great session. Renee has done a beautiful wrap-up of everything as per her delivery of the whole session. So check out those extra links and we look forward to seeing you next time. Thanks, everyone.
Don't forget to do the survey.
Exactly. Thank you.
Yeah. See y'all.